Frames of reference. So in computer graphics we distinguish different important frames of reference when we're transforming our space in order to render it. First of all, we model our objects in object space. So we saw a snowman or a cube, it's modeled in its own local space. Usually it's modeled, let's say, asymmetrically from the origin, or maybe it's modeled up from the origin. For example, this hut here, we want its origin to be down here. So a 3D artist is modeling our geometry, our beautiful hut, and keeps its origin there so that we can place it in our 3D world more easily. In order to place it or orient or scale our object, we use the model matrix. And by using this model matrix on different objects, on different model matrices for different objects, different transformations, we create our world space. So in the world we have somewhere our world origin, and when we put our objects into our world, well, they're initially all in this world origin, but then the model matrix moves them or rotates or scales them around in our entire 3D world. So the world space is kind of the root node in the scene graph. Its origin is defined by the identity transformation, and every child, every object is transformed relative to it, like this. So we have our objects, and they're all moved into different locations and transformed differently by their own individual model matrices. And somewhere we have the world's origin. And this is like in the vertex shader, we are multiplying our vertex with our model matrix first. Next we want to represent everything in the world relative to the camera. This is to make the projection onto the screen, the rendering that we see in the end, easier. So in the world somewhere we have a camera, and our goal is to transform the world so that it becomes this frame of reference. In order to do that, let's first think of the camera as just another object in our world. It has its own rotation and position. We really don't want to scale it somehow, because then we would be scaling everything. So the scale is really not relative for the camera's transformation. Only the rotation, like how is it oriented in our world, and its position, where is it in our world. Now, if we assume that, then the camera has its own model matrix that stores its orientation and its location. That model matrix of the camera would be like this. So we have the basis of the camera. So the basis vectors of that would be the columns of this linear transformation part, because that would hold the rotation of the camera. So when we have rotated it, we have transformed the standard basis, the world spaces, so that the camera has its orientation. So the transformed basis vectors, the rotated basis vectors, are the camera's basis vectors and columns in this camera's model matrix. After it has been rotated, we then also want to move it someplace. So where is it located in the world? Its position in the translation column. So it's important to remember from the previous material that the columns of the transformation matrix are the transformed standard basis. Now we actually want an inverse matrix, a matrix that transforms the world space coordinates into camera space. Because right now we have the camera's model matrix. So this is a similar model matrix that we would have for, let's say, a table or a cube. So we have rotated somewhere, we have positioned it somewhere, let's say we haven't scaled it. So by applying this matrix, we transform its coordinates relative to the world. So right now, we would transform the coordinates of, let's say, vertices in our camera space if we would have some relative to the world. But we want to do the opposite. We want to transform the coordinates of our vertices in the world relative to the camera. So we actually want an inverse of this particular model matrix. We want something that's called a view matrix. So in order to inverse this matrix, there are a couple of observations we want to make here. First of all, this linear transformation part that we have here, this is an orthonormal matrix. So we just have this pure rotation there. We haven't scaled. So remember, when we derived the rotation matrix, we kept the basis vectors orthogonal to each other and of unit length. So that's why this is called orthonormal. These columns here are all orthogonal to each other and of unit length. So this is important to finding this view matrix. So first of all, because this is an orthonormal rotation matrix, this linear transformation part, it's pure rotation matrix, then we can just transpose it to get the inverse. This was also hinted at the preliminary math tasks 12 to 14. So an orthonormal matrix and an inverse of this is just a transpose of it. So the transformed basis vectors, the basis vectors of the camera, become rows in this linear transformation part. And next we have this translation, which we're gonna invert by just negating it. So instead of moving objects from point A to B, we're gonna negate it and move them from point B to A. And lastly, we want to inverse the order of these transformations. So remember, in this augmented transformation matrix, the linear transformation part was applied first and then the translation. But now we want to do it in the reverse order. That will give us this view matrix. So we take the inverse of the camera's model matrix, which is the multiplication of these two matrices where the camera's position is negated and the rotation is also inversed by transposing it in this linear transformation part. And by applying those two transformations in this particular order, we will get the view transformation. To simplify it, well, these are the right, top and back basis vectors of the camera, and this is the negated position. Now this might seem like a bit of a weird way to define this view matrix, and you're absolutely right. So for the programmer, we would usually want to define our camera, the way we look at our world, by these parameters instead. Its position, so this is the same that we had. We still want to place our camera at some specific coordinate in our world. We want to define a point that is looking at. So where is it looking at? Let's say we have a table in our world, we have a camera somewhere, we have positioned the camera away from the table, and we want it to look at the table. So there is this, let's say, point A that is looking at. And then we have one more degree of freedom. So if the camera is looking at our object, it's positioned somewhere, it's oriented this way, then there is this roll of the camera. So how is the camera rolled in relation to this, well, this object, let's say, is looking at? This is defined by this up vector. So this doesn't have to be the top, like the basis vector of the camera space. It just has to be some vector that defines the up direction of fixing the camera's roll. And usually, if you have a world space, you want to make it like the y-axis, so that its upward is y, which is in a right-handed coordinate system where z is backward and y is up. But if you want to roll the camera, then you would change the up vector and it would roll around the direction it's looking at. Now, it's really important to remember that this sets the roll of the camera. It's not the basis vector of the camera, because defining the basis vector, the y or the top basis vector of the camera, that would be somewhat complicated. For a programmer, we just want to say that up is this way, and then that fixes the roll. In different libraries, this is exactly what is done. So you have a position for the camera, you set its coordinates. You have this up vector, you set its coordinates, and then you have a point that you're looking at, the camera is looking at. In OpenGL and the GLM library, exactly the same. This lookat command, you have to give it 3 vectors: the position, the point it's looking at, and the up vector. When we have this lookat command and its parameters, we can find the camera spaces. So this is what's happening underneath in the libraries, because in the end we still want this view matrix, right? We want to send it to the GPU along with the model matrix and multiply those together maybe, and then multiply our vertex coordinates with this matrix. So how do we get from these 3 parameters, the position P, the point A that our camera is looking at, and this up vector, to a matrix, to the view matrix? For that, we first start finding the camera spaces. So we have this direction it's looking at, this green vector. So this is basically the camera's forward vector. Where is it looking at? Now we want to find one of the basis vectors, and the easiest to find is the third basis vector, the backwards basis vector. So let's call it back, and this is just normalize P minus A. So P minus A would give us a vector that's pointing from A to P. If we were to add it to A, then, well, these A's would cancel out and we would get to P. So it's this backward direction, but we also want to normalize it. We want to make it unit length because we're looking for this orthonormal basis where, well, all the basis vectors have this unit length. Next, well, we have this back vector. What else do we have? We have this up vector as well. So we have two vectors. One is some arbitrary direction that kind of points upwards, and we have back. So now we can find the right vector. And how do we do that? Well, we take the cross product. If you take the cross product in a right-handed coordinate system between up and back, then we will get out a vector that's perpendicular to both of them, and in a right-handed coordinate system pointing right. And the order here is important. If you change this order, you would get the left vector. But we want right because we want this right-handed system. So we have backwards, we want right next. And we also want to normalize that result. Because the up vector, well, the programmer could have put anything there. They could have put a very long vector. And if you remember the definition of the cross product, then the lengths of the input vectors were also multiplied into it. So this result, while pointing right, could have any length, and we want to normalize that as well to make it this normalized basis vector. So now we already have two basis vectors. We have right and back. And now it's we can use the same technique, this cross product, to also find kind of the top vector. So when we take a cross product between back and right in this order, then we will get another vector that's perpendicular to them and then pointing well up from the camera. And here you can see that this up, if this is, let's say, the programmer just put 0, 1, 0 there, so up y axis, then that might not be orthogonal to the other basis vectors, and thus we actually do need to find the top vector that would be the basis vector up for the camera space. And this particular result we don't have to normalize because we already normalized the input. So the back was normalized, right was normalized. So this top, this is just the cross product. And now that we have this back, right, top and this point P, we can put them in the view matrix, or we could put them in the camera's model matrix and then construct the inverse of it, just like we did a couple of slides ago. And this will result in our view matrix, a matrix that we will put into the GPU and in the vertex shader code and multiply our vertices with that as well. The next space or next frame of reference we're moving to. So right now we were in camera space. With this view matrix we managed to represent all our coordinates relative to the camera. Now our coordinates are transformed like this, that the camera is at the origin and x is right from the camera, y is up from the camera, and z is back from the camera. The next space we're moving to is this normalized device space. This normalized device cube, this -1 to 1 cube. It's also called the canonical view volume. In the initial tasks that you did at the beginning of this course, the Hello OpenGL task, for example, you had this weird space where all the coordinates were from this -1 to 1. So this is exactly that space, this canonical view volume. Now to transform all these coordinates to that space, we have to transform the camera's view frustum into the normalized device cube. So this cube from -1 to 1, we have to, whatever our camera's view frustum is, or view volume, we have to change it, transform it somehow to make it this cube. Now this cube from -1 to 1, this is so in OpenGL. In other APIs it might be a bit different. I think in DirectX the Z length was from 0 to 1, not from -1 to 1. And this is the job of the projection matrix. We will talk about projections later on, but right now know that there is this thing called orthographic projection that defines the camera's view volume as this big box with this top, bottom, near, far, left, right planes. So it's this big box, and this gets squished down to this -1 and 1 cube. Then there's also perspective projection. Now for that projection we have this frustum shape, kind of this pyramid with its top cut off, and that will get transformed into this normalized device cube space. We will see later how this is actually done. But while doing this, it's interesting to note that the objects inside this frustum kind of get deformed for this cube, or this normalized device cube. In order to see this, I have this example here that kind of illustrates this. So in this example we have this sphere, box and cone, so maybe it's better to see them as wireframes. Then we have this perspective camera with its view frustum looking at this interesting art installation. And then I've transformed this frustum into this -1 to 1 cube and transformed all of the objects inside it. The top left view is what the camera sees by the default pipeline, and the top right view is just an orthographic projection of that cube onto a screen. So you can see that they're identical. So this is kind of this proof of concept that it actually worked. But what you can notice is that when these objects get closer to the camera, for example, right now this sphere is coming closer to the camera, it kind of gets bigger in this normalized device space. Or now this box is getting closer, it gets bigger. Or this cone gets bigger, and when they move away from the camera or rotate away, then they get smaller. So this is what we would actually see in the real world. So objects further away would get smaller and objects closer by would get bigger. But mathematically, to make it seem like realistic or do the perspective projection in computer graphics, then we have to squish this geometry and enlarge it and then project it to a screen, and then that's how it works. And this is why these objects kind of get deformed in this particular case. Now we also want to flip the z-axis because our near and far planes have positive values. When we define our near and far planes with APIs, it's easier to set like positive values. So 1 unit away from the camera, let's say, is our near plane, and 100 units away from the camera is our far plane. But if you think about the camera's spaces, then well, the z-axis is pointing away. So in order to actually get the correct coordinates, then we kind of flip the z-axis at some point as well. Now this is the job of this projection matrix, and together with point normalization for the perspective projection, which we'll see later. But just remember that at some point when we're moving from camera space to the normalized device space, then we take this camera's view volume and squish it into this cube. And this is what the projection matrix does together with this point normalization. So this point normalization, where if you have this homogeneous coordinates, 4 coordinates representing a 3D point, we divide the first 3 with the last one, and we will get an actual 3D point back. This is done automatically by the GPU right after this matrix vector multiplication. Now to get a better overview of the pipeline, so in the vertex shader we have this code, projection matrix times the view matrix times the model matrix times the vertex. So all the vertices are first transformed from their local space to world space by this model matrix. Then in the world space, the coordinates have to be transformed into camera space by this view matrix. And then we want to squish this cube, or this view volume, into this cube with this projection matrix. And this is what this row does. And this kind of transforms the object's local space. I've written here clip space because this point normalization, this comes a bit later. So what's happening in the pipeline is that we do this transformation, and now we're in this clip space. And the next step in the pipeline was this culling and clipping. So culling was determining the front-facing triangles and culling the back faces, but this clipping helps us remove the vertices that are not inside the view volume. So let's say our geometry that we transformed through these 3 matrices, these 3 transformations, happens to now lay outside of our view volume. So we are not actually seeing this cube or this table that's outside of our view volume. So it doesn't make any sense to keep calculating stuff on these vertices, to keep parsing them, because we won't see them anyway. They will not be on the screen, so we can just discard them. And sometimes it might happen that we might have a triangle that's halfway inside the view volume and halfway outside. And this is where this clipping is performed. So we clip this, we kind of cut this triangle such that it ends at the edge of the view volume, and maybe we need to add some new vertices there to rasterize it correctly, but we don't need to spend additional resources on vertices that lie outside of the view volume. And then this division by W, this moves us from this clip space into this cube, and from this cube we can just orthographically project everything down and scale it up to the viewport space, to the screen space. So to recap, we start with our objects in object space. We use the model matrix to represent them relative to the world space. We then use the view matrix to represent them relative to the camera space. In that space, often the light calculations are done. We will see this later on in the materials, but what color should the pixels on this triangle be? We can calculate this, and this is usually done in the camera space. We can also do it in world space, but some of the things are a bit simpler in camera space, and traditionally people do it in camera space, but you could also do it in world space if you really want to. Next, we use the projection matrix to move into this clip space where things lying outside of the view volume get discarded, and things halfway in the view volume get kind of clipped, and then the part that's outside will get discarded. Then this homogeneous division is performed, which finally takes us into this normalized device space, into the canonical view volume cube, this -1 to 1 cube, and then there's just another very simple transformation to project the cube onto the screen, and this takes us to screen space. These last steps, this division and this screen space transformation, they're done automatically in the GPU already. But these first steps, the projection matrix, the view matrix, and the model matrix, these are what the vertex shader is responsible for. And this is how the code of the vertex shader looks like. The vertex shader code must return homogeneous coordinates in the clip space, that is this normalized device space, without the W division. Now it depends how you actually implement this. You could send in the matrices as projection, view, and model, and then multiply your vertex coordinate with those like this. Or you could start multiplying the matrices, the model matrix, view matrix, and projection matrix already together into less matrices. So for example, it could be projection matrix times the model view matrix, or the model view projection matrix. Now often this second version is good because this takes your coordinates into camera space, and in camera space we can calculate light, the lighting calculations also in the shader. So very often you need the coordinates to be in the camera space to do the light calculations. But in the end, this GL position, this output of the vertex shader, this must be the projection matrix times the model view matrix times your position. And this is also why we have this vec4 here, because it's homogeneous coordinates. The model view and projection matrix are all 4x4 matrices. They include translation, which is why you need the 1 back here. And after it, the GPU automatically does W division and screen space transformations. Now, from this video, you should understand the local space. Objects are modeled in this local space. There's the model matrix M that transforms the objects. The world space, which is created by moving the objects into different locations. The view matrix V that transforms the world space into camera space by representing everything in relation to the camera. And in part of that, you should also understand how this view matrix is constructed from the lookat command parameters. And after it, we had this normalized device space, or this canonical view volume, the screen space. And based on that, you should very clearly now understand the job of the vertex shader and this large matrix vector multiplication. That is the main job of the vertex shader code.